the question is, what are the A1, A2, all the way to AN, so that V equals to A1 V1 plus A2 V2 plus da 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 AN VN. In other words, you want to be able to figure out what the linear combination should be for any given vector V if you have an orthonormal basis. So how do you get A1, A2 until AN? That's the question. Okay. So the answer for this is simply that you have, you just have to calculate the inner product. So let's see what happens if we assume that we already have this. Okay. So assume that there's some coefficients A1 through AN so that V is represented by that. And we know that's possible because it's a basis. Basis spans every vector in the vector space, right? So there should be some values here. So if we assume that V is already that, then we can stick in this right side into V. And then use linearity to just expand, right? So it's a bunch of additions and some scalar multiplication. So we can rewrite this as A1 V1 V1 plus A2 V2 V1 plus da 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 AN VN V1. Okay. Now what is V1 V1?
Magnitude squared.
Which is?
1.
1, because we have an orthonormal basis, right? So A1. What's V2 V1?
0.
0, because it's orthogonal. Right? Perpendicular vector is when you do the dot product, inner product is 0. So that's gone. The next one will be gone. This one also will be 0. So you just have A1. Oh, that's nice. A1 can be obtained just by taking V inner product with V1. Why was this possible? Only because it's an orthonormal basis. It's not possible if it's not orthonormal basis. All right, so now let's think about this one. V2. What do you think this would be if you do the same exact thing?
0?
No.
Oh, wait, sorry.
V with V2. So you stick in this into V, right? And then expand just like before. Then instead of V1, this will be all V2. V2 here, V2 here, V2 there. What's going to happen? A2 will be the only survivor. Everything else will be 0, right? So you'll just get A2. Oh, so you have a really simple answer, which is that AK would be V, VK, for K goes to 1 until N. Done. And you have the following identity, which is V should be equal to K from 1 through N of V, VK, VK of VK. You multiply this to VK. But these are the AKs, right? So this is always true. Let's try this problem. Okay, first, how do you show that it's orthogonal? Sorry. You have to show that B is orthogonal under the regular inner product, the usual dot product in LT, okay? But I think it should be clear, okay? So how do you show it's orthogonal?
Do the inner product or the dot product and make sure it's equal to 0.
So if you do the dot product or the inner product, this is 2 times 1 plus 2 times 1 minus 4, which is 0, right? We see that that's 0. And then 1, 2, 2 with 2, negative 2, 1 is also 2 minus 4 plus 2, so it's 0. And then 1, 2, 2. Oh, so I know that these two are orthogonal, these two are orthogonal. Now you just have to check this one is orthogonal. So 2, 1, negative 2, dotted with 2, negative 2, 1. That's again 4 minus 2 minus 2, which is 0. So these two are orthogonal. So I've checked all pairs, and they're orthogonal to each other. That's okay, right? Now part B. How do you normalize?
You divide by its magnitude.
Yeah. So you take that vector and divide by its magnitude. What's the magnitude of a vector?
It's
Square root of 1 squared plus 2 squared plus 2 squared. Well, what's that? 1 plus 4 plus 4? That's
3.
no, 1 plus 4 plus 4. Oh yeah, it's square root after
Yeah,
square
sorry,
root, and it's 3.
yeah.
Yeah, you're right. Yeah. So you have that. So you end up getting 1/3, 2/3, 2/3. Okay. And now what you have is you kind of see that after squaring, all these numbers are same. The square sum are all 9. So if you take the square root, it's 3, right? So now you see that the basis, another basis, let's call this A. The basis A would be 1/3, 2/3, 2/3, and then which one is it? 2/3, 1/3, negative 2/3, and then 2/3, negative 2/3, 1/3. That will be on the orthonormal basis because I've normalized everything so that it's size 1. Right? Okay, so now comes the important part. How do you represent 1, 2, 3 as a linear combination of those? So the question is, I want 1, 2, 3 as something times 1/3, 2/3, 2/3, plus something times 2/3, 1/3, negative 2/3, plus something times 2/3, negative 2/3, and 1/3. That's what I need. And of course, you can put this as x and y and z, and then come up with system of equations 3 by 3, which will take a long time. But because our matrices are orthonormal, it's a lot easier, right? How do we do it? We just take 1, 2, 3, do a dot product with 1/3, 2/3, 2/3 to get what it is. And what's that? It's really 1/3. You can factor the 1/3 out and just do 1 times 1, which is 1, 2 times 2, which is 4, 3 times 2, which is 6, so 11/3. Done. That's going to be 11/3. Now let's do the other one. 2/3, 1/3, negative 2/3. Again, factor the 1/3 out, and you have 1 times 2, which is 2. 2 times 1, which is 2. 3 times negative 2, which is negative 6. And we get negative 2/3. So this is going to be negative 2/3. And then, now for this one, this last one, I guess I can just quickly do it. It's 1 times 2, which is 2. 2 times negative 2, which is negative 4. 3 times 1 over 3. So what's that? That's 1/3. So this is the answer to the last one. And the answer to this, again, I want to stress that it was possible to get it so easily because the system of vectors that we had, the basis vectors was an ONB. Okay?